Hello and welcome back. In this video we're going to talk about equilibrium, get an introduction to equilibrium. Previously when we talked about kinetics, you saw a graph that looked something like this, where we plotted concentration versus the reaction as it proceeds. And for kinetics, I told you that we would focus on the very initial part of the graph, where actually this was time. And the slopes of these lines represented the rate of the reaction, and that's kinetics. Now notice as time progresses, there reaches a point, or the reaction reaches a point where everything doesn't change. Everything remains constant. This is the state of equilibrium. What exactly is it that causes this graph to come out this way? Well, let's take a look what has to happen. In a closed system, so everything is contained, and if we have this reaction of A plus B goes to C plus D, as the reaction proceeds and keeps going to give products, there's going to come a point in the reaction where we now have so much product built up in this closed system that now the products can be colliding with each other as well, since they are in such high amounts at some point, or high enough amounts at least, to where the reverse reaction will also be taking place. So now we're having opposing reactions happening at the same time. And when they reach a point where the rate of the forward reaction is the same as the rate of the reverse or the back reaction, this is what we're going to get. The overall concentration of all the species, they're being reacted at the same rate as they're being produced, hence their concentrations remain constant, or partial pressures. So there is a law of mass action, it's called, and what we can do is write an expression for these concentrations, or actually their activities. So let me make some room here. And as far as the equation, or the law of mass action, you have a capital K. Now you have to be careful that you don't mix that with the rate constant, lowercase k. This is the equilibrium constant K, is equal to, and this is the technical definition that I'm giving you, activity of all the products over the activity of all the reactants. Now, what exactly is activity? Well, it depends on the substance. The activities for, if you're dealing with a solution, the activity is equal to it's called an activity coefficient, times the concentration of the substance, of the solute. For a gas, the activity of a gas is going to be the partial pressure of the gas divided by standard pressure. Okay, this is very technical. You're not going to find this in your textbook. But let me tell you where we start in the textbook in terms of what I've just given you. For general chemistry, we go with this right here, where we assume that the activity coefficient is equal to 1. Something else that you need to know, activities are unitless. Okay? So, what then activity for a solution is going to be, I've run out of room, let me write it out here and then we'll come back. Activity for something in solution is going to be equal to, approximately, and now the activity coefficient drops out because it's equal to 1 as far as we're concerned, is going to be the same as its concentration. Now, in order to make it unitless, it's effectively like saying we're dividing by standard concentration, which is 1 molar. So then the concentration unit cancels, and it's just the value of the concentration that will be used in our expression. Okay, and as far as the gases go, the activity of a gas is its partial pressure over standard pressure, and that's to get rid of the units. For our purposes, we're just going to use the partial pressure without its units and not having to divide, because effectively you could be dividing by 1 atmosphere and it changes the, it gets rid of the unit for pressure. So we are going to use unitless values for the equilibrium constant. Now, the last possibilities, we talked about solutions, we talked about gases, we didn't yet say anything about solids and liquids. So something in the solid or the liquid, the activity is simply 1. Okay? And so when we are writing the equilibrium constant expression, we will write it either in terms of concentration, or we can write it in terms of partial pressure if everything is a gas. And we will not include in the expression solids and liquids. So let's apply now. This is the conceptual basis for the equilibrium constant. Now let's apply all these things that I've just shared with you, and we are going to then write the expression for this reaction. So let's write the equilibrium constant for this reaction. Let me change it just slightly. Let's say we have A moles of A plus so many B moles of B, C moles of C, and D moles of D. And also, when we're dealing with equilibrium, the arrow is written as half arrows like this. And that means equilibrium. Those are the equilibrium arrows. So now our equilibrium constant expression would be K is equal to, we need to do product. So we have concentration of C and is raised to its coefficient times the concentration of D, whoever that product is, raised to its coefficient, divided by the reactants. So we have concentration of A to the 8th power times the concentration of B to B. And that would be the form of the equilibrium constant for, or the expression of the equilibrium constant for this particular reaction. Now let's take a look at some specific reactions and write down the equilibrium constant expression. I'm going to give you a couple of these and give you an opportunity. You could stop the video and write the expressions, and then we'll come back and see what you get. So for one of them we have, let's say we have nitrogen, this is gas, plus 3 moles of hydrogen, gas, at equilibrium with 2 moles of ammonia, gas. And the other equation or reaction equilibrium that I want you to write the expression for is hydrogen gas plus fluorine gas at equilibrium with 2 hydrogen fluoride gas. Okay, so pause the video and write the expressions of the equilibrium constants for each of these, and then come back. Okay, the equilibrium constant expression will be K is equal to concentration of products. These are the products. We have ammonia squared divided by our reactants, which are nitrogen. We have only 1 nitrogen, so we have power of 1. And then we have hydrogen. There are 3 moles of hydrogen, so it's hydrogen cubed. Okay, and for the other, for the second reaction, or equilibrium, we have K is equal to, now the products, which is HF, and we have 2 moles, so it's squared, divided by the concentration of hydrogen times the concentration of F2. I said the concentration of products over the concentration of reactants. And I've also talked about two different reactions going on, the forward reaction and the back reaction, right? So which reactants and products do we mean for the equilibrium constant expression? Well, it is reactant at equilibrium with products, or reactants and products. So in other words, it's reactants and products with respect to the forward reaction always. So when you write the equilibrium constant expression, focus on the way it's written, and whatever's on the left side of the reaction, these are the reactants. Whatever's on the right side, those are the products, and that's relative to how you write the equilibrium constant expression. Okay. Now, what exactly is the significance of K? What information does it communicate to us in terms of the chemistry? Well, if we consider that K is the concentration or partial pressures or activities, however you want to think of it, of products over the concentration of reactants. So that's the basis for what the equilibrium constant is. If the value of K is larger than 1, what exactly is that telling us chemically? Well, if the K value is greater than 1, this is a ratio, that means the numerator or the products are greater than the reactants. That means the products, if there are more products than reactants at equilibrium, it means that the products are favored. Or the reaction that produces product is forward reaction, so the forward reaction is favored. Now, what does it mean if the value of K is a small value, is less than 1? Well, if it's less than 1, it means that this ratio is less than 1. That means the numerator is less than the denominator, or the reactants are in greater amount. That means the reactants are favored. And the reaction that produces reactants would be the reverse, or the back reaction is favored. And what happens if K is equal to, somewhere close to, or pretty close to 1? That means neither the reactants nor products are favored. They're about the same. So you have neither or both reactants. And let's say both reactants and products are equally favored. There are very few reactions. I don't know that we will come across too many, if any, of the equilibrium situations where we get an equilibrium constant that's equal to 1 or close to 1. But these are the general things that we get, or as far as equilibrium constant and the information that it is communicating to us about the chemistry of that equilibrium. The word favored is thermodynamic, and as we keep going in our studies, we're going to look at thermodynamics and see what favorability really means from a thermodynamic standpoint. There is a thermodynamic function that we are going to learn that talks about favorability. And that, my dear students, wraps up our video on the introduction to equilibrium and the equilibrium constant.